Welcome to the third videos in image processing using fractional calculus, or as you can see in the name of this title, it's called the calculus for the 21st century. Okay, so I will contrast and compare between the classical method calculus versus the fractional calculus. Show you many examples between the two. Okay, so I want to start with the equation number one that I have written down here. That is called the Leibniz rules for differentiating uh, underneath the integral sign or with the integral somewhere nearby. Okay. All right. So let's take a look at the left-hand side of equation one. You have a differential operator dx, so that's a local operators, and acting on the integral with the variable limits. So instead of having constant, it's a function of x. Okay, and then the integrand is inside the integrand is f of x comma tau, and then d tau. So that's the left hand side. So it's gonna equal to the partial derivative of the integrand with respect to x and dt plus. So in a way, the differential operator dx and the integral sign, they cancel out, and so what you do is you put the upper limit of b of x uh, into tau. So that's why I have f of x comma b of x, and then I have to take the derivative of the b of x with respect to x. So I have to take the derivative of x of the upper bound of the integral, and then minus again f of x, but this time I put the lower bound a of x into tau, and then I have to take the lower limit derivative with respect to x. Okay, so we're gonna use this a lot. Okay, the other equation that we use a lot too is this equation here. Is sometimes they call this the Cauchy integral formulas, but it's just saying that if you have a multi-integral object like this, so in this case it's an n-fold integration with the volume form of dtn. So it's like an n-dimensional volume integral of some function. This can be replaced by just one integral with this factor 1 over gamma of n, or n minus 1 factorial, the integral from a to x, and then this here, the x minus tau, is called the kernel of the integral, and then raised to the n minus 1, and then you put that image or the function f of tau d tau. So this is the right hand side is equivalent to the left hand side. Okay, so this is one way to simplify things. So equation 2 is also often used. Okay. Very useful. Okay, what I do next is I'm gonna define some term. So I'm gonna define capital D is equal to the differential operator with respect to x. And with that, according to the fundamental theorem of calculus, this operator D act on this a to some x power f of c dc is equal to just f of x. Okay, so to prove this proof, I consider equation 1 equation 1 Okay. Okay, so according to equation 1, we have this d by dx of this a to the x f of c dc. Remember, the equation 1 tells you that it's going to be the integral of a to the x partial f of c dc partial x, and then plus I'm gonna replace the c f of c with f of x, and then I'm gonna have to take the d of x dx. Okay. Well, the font is a little weird. Okay, so it's gonna be f of x dx dx, and then the other term is minus f of a, and then dA, which is a is a constant, so dA dx is 0. And then this term here too is 0 because the function f of c is independent of x. So therefore you left with just f of x, and then dx is just 1, so therefore you just have that. Okay. So this is equal to d, the integral of a to the x f of c dc. Okay. So this here is just a result of equation number 1. All right. However, if you switch this order, so instead of having a derivative on the left, you're gonna have a derivative inside the function first. So if you have a case like this, suppose you have a to the x d of f of c f of c dc. Suppose you have that, okay? Yeah. Okay, so would this still give you f of x? Well, if you really expand this, you can rewrite this a to the x d as d of c of f of c dc. But notice that the differential dc cancel here, so you left with just a to the x d of f of c. Okay. Okay, so now here, just like when we have an expression like this, d of x from 0 to t, let's say, then this integration will give you x, you add to x, and then put in the limit of integration t, so this can be t minus 0, just t. Okay, so think of this f of c is like this x here. Okay, so this is x here, so the integral here would become f of c, and then the limit of integration is x, right, go to x. So by this I mean you plug x into the c, so you have f of x minus f of a. Okay, you see what we have here, right? If the derivative is inside the integral to start, then we're gonna pick up some extra term. You see, and the extra term is this minus f of a here. Okay. So in other words, the two operator, they are they are non-commuting because of the extra term. Okay. Okay. This extra term right here, extra term. In physics, they call the extra term. Sometimes they call the extra term the transient term. Transient. And will take on different values depending on the initial conditions and the boundary condition of the problems. Okay, but normally this thing here would die down as you integrate from one end to the other. Okay, so let's move on. So we're gonna define something. We're gonna define the integral. Define this as the integral. So the derivative is when you have a positive term. So when you have a negative term, negative alpha, let's say. How about just 1? Okay, just 1 right now. D to the minus 1 from a to x of some function of f of x. This is defined as the integral of a to x f of c. Notice I'm changing the x to c here because it's just a dummy variable, so I could call it anything. So the differential there is also a dummy variable. Okay. Okay, so if we start with this as a definition, let's call this here equation 3. Okay, so I'm gonna box this. Okay. Okay, so if we have that, then what does this mean when you have a d, like a derivative on this? Okay, remember d is by definition is defined to be just the differential of x. Okay. All right. So here we have the case where the differential is going to be outside of the integrals, so it's going to require us to use the rule in equation number 1. Okay, so what is this equal to right here? You would think they cancel out, right? Let's see if this thing will give us any special terms. Okay, so we're gonna have a d by dx. That's d right here, and then this part right here is defined up here to be a to the x f of sigma d sigma. Okay, so since this thing here d is outside the integral, then this thing here, you could say that this here is gonna give you, yeah, this can be partial sc dc partial x plus f of x, and plug it in for x into c. Okay, this, and then dx minus f of a dA dx, but a is just a constant, so this is 0. And then of course f of c is independent of x, so this goes to 0 as well. So then what you have is d on d minus 1 a to the x f of x is equal to just f of x. Dx by dx is just 1. Okay. So these two, d to the minus 1, which is the integral, is a right inverse to d. Okay. Unrestricted right inverse to d. So let's call this here. Let's call this here equation 4. Equation 4. Okay. Okay, so you could here's a remark for it. So d to the minus 1 a to the x is unrestricted right inverse unrestricted inverse of operator d. Okay, so now what would happen if d and d minus 1 reverses? So that's gonna be the next formulas. So instead of having d first, you're gonna have the integral first, d to the minus 1 a to the x and d to the f of x. Will this still give us an f of x or something else? Okay, so this here, you're gonna have the integrals. Let's see. Yeah, so they're gonna define this way. So we're gonna use 4. So equation 4. Nope, not 4. We're gonna use the integral of a to x. Then d by d tau of f of tau, and then d tau on this side. Okay. Okay, so the d tau cancels. So you have the integral of a to the x, the differential of f of tau. Okay. So the formula to integrate this is that whatever is inside this d here, you could put a parenthesis here. Whatever inside that d there, that would be the answer for the integration. So it'd be f of tau, and then you put in the limit of integration from a to x. So now I'm going to put the x into tau, f of x, minus the lower limit, a into tau, so that'd be f of a. So clearly, when the order of the operators reverses, sometimes we pick up extra terms, the extra transient term. Okay. So let's call this here equation 5. Okay, so let me box this. Okay, equation 5. Okay, sometimes they call this here the transient term, or the initial data, the boundary conditions will dictate what type of value you have for this f of a, the extra term. Okay, so let's do some example here. Okay, so sometimes the extra term f of a is specified by the boundary condition. By initial condition or boundary conditions. Okay. All right, so let's do an example here. Let's define, for this next example, let's define D, define D to the minus 1, A to X, f of X, as equal to f of X, with f of A equals 0 due to, some initial condition. So what is the value of, by induction, what is the value of D to the minus 2 X, f of X? This is going to be a to the X, and then it can be another integral of a to the C prime, and then what you have is f of C dc, and then dc prime. Okay. Okay, so you can see here that the first integrations over f of C dc will give you some function of capital F of C. Let's see, f of this, f of C, and then you plug in the limit of integration, C prime, A to C prime. So then this reduces to A to X, f of C prime minus f of A. And all of this is being multiplied by dc prime, which is the other volume elements outside of the other integral. Okay, so here you could use the linear properties of these functions, and you could separate this into two integrals. So this becomes a to the x f of c prime dc prime minus f of a is just a constant, so you could pull that outside of the integral, a times x, and then dcx. Okay. All right. So this here, so the left hand side is a d to the minus 2 x on some function x. This f of x can be the image of the picture or something, equal to what does this integrate into? Well, this here will give you some bigger f. How about squarely f, like f of c prime evaluated at x a minus f of a, and this here is just a c prime with the limit of integration of x to a. Okay, so this is equal to the first term on the right hand side. I'm gonna stick the x in here, so I'm gonna have a f of x minus so I put a into this c prime, so f of a. Okay, and then on this side, the second term of the right hand side is going to be minus f of a, which is a constant, and then put in the limit of integration, so that would be x minus a. Okay, so the answer to this here is, since you don't have any operator acting on this here, you could assume that there's a d0 here acting on this f of x, and then this is the boundary conditions for the initial condition for the functions, minus f of a, and then this is the other part, the extra term, and then this here is a d to the minus 2x f of x. Oh, I see. I made a mistake right here. This should have been that right there. Will give me f of c prime, because this part here is 0 right here. Okay, so I don't have to do that integration. This is 0. So this will becomes so this first term on the right hand side is going to be f of x minus f of a, but we already specified that this thing here is equal to 0, so therefore a to the minus 2x f of x is equal to f of x. Okay, so what equation is this? Equation 6. Okay, so the next one, the next property is going to be, suppose you have a d raised to the p power on some f of x. Okay, so this can be written as d of p, and then you can always insert a d times d minus 1. See, d by itself is understood to be d to the 1 power. So therefore, this d to the 1 power and d to the minus 1 power, when you multiply them, you get d to the 0, which is like a 1, okay, on f of x. Okay, so this is the 1 here. Now I'm gonna combine the p and the 1 together. So d of p plus 1 times d a to the x minus 1 f of x. Okay. And then I can always insert another d and d to the 1 and d to the minus 1. So what I would end up having is this. So d to the p plus 2 going to be dax to the minus 2. Because when you add these two power up, you're still going to get p at the end of the day. Okay. So even if you go to the n power, so you do it n time, then you get d to the p to the plus n time is equal to a to the d to the x minus n time f of x. Okay. So then the p derivative of f of x on the left hand side is equal to d to the p plus n derivative. This is the ordinary derivative right here, and then this is a to a minus n of x. Box this. So this equation is cos 7. Okay, now you can alternatively, instead of starting with the p derivative of f of x, you could say, let's say you have a d to the so you have d to the minus p. So this is an integration here, okay, of f of x. This here is the same thing as d of m, ordinary derivative. So dm is d by dx, like that. Dm times dA to the x minus m minus p plus m. Now you can see the power. If you add up in the exponent, then you get m minus m, so that's 0, and then you're left with the powers of minus p, which is the original power that you have here. Okay. So f of x, like that. Okay, so let me box this. So d to the minus p of f of x is equal to the ordinary derivative times the okay. So let me box this. Equation 8. Okay. All right, so here are more properties on these two operator, the local ordinary derivative versus the non-local fractional integral. So suppose you have let me write this a differentiation. Uh, let okay, let I let D equal differentiation operation. Then let I equal integration operators. So suppose you have a like a D to the M and then you have another D to the N on some function f of x. Okay. Actually, I don't need to put that function, test function there. This here will just equal to the final result is going to be D, and then you have M plus N. So this obey the exponential law. Exponential law. I'm going to box this too. Okay. So instead of doing each box, I'm just gonna write them all together. So if you have, okay, so D acting on Dn, then the resulting operation is going to be D to the M plus N. If you have D M and integration to the n power, okay, or D to the negative n, then this here is equal to, depending on the magnitude of m and n, so it's going to be differentiation of m minus n. So this object will become a derivative if m is bigger than n. M is greater than or equal to n. Okay. And then if you have, let's see, an integration and integration, so I of m, let's say, on another integration operators, and I missed the first part right here. So here's another component to this. So dm and in, if n is greater than m, then you're gonna have integration n minus m. So this here is if m is less than or equal to m. Okay. And then if you have two integration operators, then this will be integration m plus n. And then the last combination is you have an integration of m and differentiation of n. This will be more difficult to obtain because of the extra term. So this will be harder to get to work out, but it's doable. So here is an example of a case where you have integration first and then differentiation second on some function, and then we're going to see some where the extra term come out. Okay, suppose you have d of minus 1, right? D of minus 1 is you know that that's going to be a fractional integrals. How about this? From now on, d a to x to the minus 1 is just, I'm going to call this here just d to the minus 1. Because I don't want to write the base index every time that we have something. So d minus 1 on differential 3 on f of x. Okay. So what is this? Well, according to the formulas, this here is just going from a to x, d3. This is the third derivative with respect to f of, let's say, c or something. F of c dc. Okay. All right. So whenever you have this, you can rewrite this as, you could pull out one of the d, like d to the 1 power. So what you left is d to the 2 power of f of c. Okay. Well, d to the 1 power is the same thing as d to the c 1 power. Okay. So then this here becomes 0x. D to the 1 power is d of the square of f of c dc. Now you see the cancellation of this differential dc and this dc here. So you left with 0, the integration from a to x of d squared of f of c. Okay. Well, we know how to integrate that. Anything that is in this parenthesis here is going to be the answer to that integration. Is going to be d squared f of c, and then my limit of integration is going to be going from a to x. So therefore this is equal to the square of f of x minus the square of f of a. Okay. Now, yeah, so we're almost done here. So the end result is that d to the minus 1, which is the integration, act on the derivative, the ordinary derivative of f of x, is going to be d squared of f of x. Notice we're going to write d squared of f of, when you have a constant inside the function, then you write this as f double dot a. Okay, so this is minus f double dot a. Okay. So I'm going to box this. So which equation is this? 10. So this is going to be 11. Okay, so this is 12. So you see the extra term is this f double dot of a here. Transient term. Okay. I'll do another one. How about let's do d to the minus 2 on the third derivative of f of x. Okay. So this thing here will give me from 0 to x. Should I use x or c? Okay, x. So a to the x. And then I'm gonna use another a to the tau prime, c prime, and then the function is d3 of f of c dc, and then dc prime. Okay, because the factor of minus 2 here will give me twofold integration. Okay, so now it's going to be 0 a to x, a to c prime. Notice we're going to take out one of the d and write like this: d to the c of d2 f of c dc, and then dc prime outside. So if we do this integration, this thing here will becomes, this cancel this, so we left with just a to the x, a to the c prime, and then this here is just d of on this, which is d of e squared f of c, and then I have a dc here, dc prime here. Okay, so this integrate to a to the x, this integrate to just whatever inside this parenthesis, and then you plug in the limit of integration. So it's going to be d2 f of c, and then evaluate it at c prime and a. So this will be the integral of a to the x d squared f of c prime dc prime, and then minus the other one is going to be a to the x d squared f of a. This is a minus subtraction, minus f of a dc prime. Okay, since this object here is just a constant, it's been evaluated at f of a, you can bring this part outside the integral. Okay, so the first one on the, let's see, the first one on the right hand side is going to be, I'm going to take out another d, so it'll be a of x d of c prime, and then I have a d of f of c prime, d sigma prime. And then the second term is going to be, I could bring out the constant term, so I have minus d squared of f of a with the integration a to x dc prime. Okay, now this cancel this, so I left with a to the x d of d f of c prime. Okay, well, that's easy to do. The answer to that term is this term here is just d of f of c prime evaluated at a to x. minus the second term, minus d squared f of a, which is a constant term. And then this right here, the integral here would become c prime, because whatever inside this differential is going to be the answer to that integration, evaluate at a to x. So now plug in the limits. So you have d of f of x minus d of f of a, and then over here is going to be minus d squared of f of a times x minus a. Okay, and remember that d on a function that is being evaluated at the point a, constant point a, this is equal to f dot a. Okay, so this become d f of x minus f of a minus d squared f of a is going to be f of double dot of a times x minus a. Okay, so the result for this d2 d minus 2 on d3 f of x is equal to d1 of f of x minus f of f dot times a minus f of double dot times a times this x minus a. Okay, so I should box this. This here is equation 13. Equation 13. So let me see what are the extra term. The extra term is are these right here, the transient term. Okay, so for as an exercise for you guys, so for an exercise for you awesome people, I'll give you the answer. D minus 3 d3 f of x is equal to d0 of f of x minus 1/2 f double dot of a times x minus a squared minus f dot of a times x minus a, and then minus f of a. Okay. So your exercise is to follow what I did up here and show that if you have this combination of the the integrals and the derivatives, you're going to get an expression like this. Oh, I boxed it wrong. Oh, that box is kind of weird looking. All right, so I'm just going to call this 14. Equation 14. Okay, so in general, if you have integration first, and that's integration n, and differential derivative to the power m. This here is equal to, you have two outcomes, so it's either going to be differential if m is greater than n, if m is greater than n, and then it's going to be integration if n is greater than m, if m is less than or equal to n. Okay, so that's in general, that's what happened if you have this combination. I have a few remarks. So anytime you have so here are my remarks. So d to raised to any integer power, this here is considered a local operators. And anytime you have integration raised to some integer power, this is non-local. Operators, non-local or global, if you want to call that. Okay, let's do example here. Example, this example is from 19th century calculus. Whether the order of the operation is integer values. Okay, so suppose you have dm of some x raised to p power. Okay, remember dm is just d by dx m time. Okay, so that means I have to differentiate this p, this function here, m time. Okay, so for example, if I do this as a first integration, so I have d of m minus 1 on d by dx of x to the p power. You know, the answer to this is going to be d to the m minus 1 time p and time x to the p minus 1. Okay. You just bring down the power of p and then you subtract 1. Now if I keep doing this m time, then this is what I would get. So I would get p, the next term is p minus 1, p minus 2, and then all the way to p minus n minus 1. Okay, so that means I'm going to get the x to the p minus n minus 1. Minus n. Yeah. So I'm going to rewrite this as p minus 1 all the way to p minus n plus 1 plus 1. And then I'm going to write the x to the pn over here. So now if I see the next term here, if I put in the next term as p minus n plus 1 minus 1, then I just have p minus n. And then the term smaller than that would be p minus n minus 1. And this goes all the way down to 1. Okay. So since I have p times p minus 1 descending order like this, this whole thing here is equal to p, this whole thing here. P factorial. Okay. So since I add in this p minus n all the way down to 1, I have to divide the same p minus n minus 1 all the way to 1. It turns out that the denominator is really p minus n factorial, because it's going from that value to 1. And then the top is p factorial. And the power is x to the p minus n. Okay, so dm of x to the p. Now we could rewrite this in terms of the gamma function. That's fine too. So dmxp equal to gamma of p plus 1. Right? Gamma of p plus 1 is p plus 1 minus 1, or p factorial. And then the p minus n factorial is really gamma of p minus n minus 1. Oh, plus 1, I mean, plus 1. Then x to the p minus n. Oh, this is m, sorry. This is m. This is m. This is p minus m. The p minus m. Okay. So I'm gonna box that. Call this equation 15. Notice here's another remark too, is dm on x to the p power is equal to 0. That is equal to 0 when the value of m greater than p. Okay, so the other way is what happened if you have minus values, like d minus 1 on x of p. Okay. Okay, so by the definition of this, this is the same thing as d minus 1a to x of p, and this is equal to 0 to, I'm going to go from 0 to x. So I'm going to replace x by c because it's just a dummy variable. So c to the p dc. So when you integrate this x to the p, you get c to the p plus 1, and then divide it by p plus 1. Evaluate it 0 to x. So therefore this is equal to x to the p plus 1 over p plus 1. So now you see the pattern. If you have d to the minus 2 of x of p, that means you're going to have 2 of these integration, 0 to x, and then 0 to c prime. So I have cp dcp, I mean dc, and then dc prime. Okay, so let's see the first one, the first integral here. So that one will give me 0 to x. It's going to be cp plus 1 over p plus 1. Divide, the limit of integration is 0 to cp prime dc prime. Okay, so equal to the integral from 0 to x. Plug in the limit of integration, so c prime into c. So prime raised to the p plus 1 over to p plus 1 dc prime. So now I just do this second integrals. So this 1 over p plus 1, that's just constant, so I could pull it out of the integral. And this here is c prime to the p plus 1 dc prime. So the integration of this is going to be 1 over p plus 1 times c prime to the p plus 1 divided by p plus 1 plus 1, which is p plus 2. And then the limit of integration would be 0 to x. So put x into c prime. So then I have x raised to the p plus 2 divided by p plus 2 and p plus 1. So the pattern that you see would be like this. So you have d to the minus n of xp. Okay. So then you would have 1 over p plus 1, p plus 2, p plus n. The power is going to be x to the p plus n, like that. Okay. So I'm gonna rewrite the order in the denominator. p plus n first, so it's going to be 1 over p plus n times p plus n minus 1, all the way down to p plus 1. And then the next value lower than this would be p, and then p minus 1, all the way down to 1. So this part right here is p factorial that I need to multiply downstairs. So I need to multiply upstairs with the same factor. So the top would be p factorial times x to the p plus n. Okay. So I'm ready to box this. So d to the minus n x of p is equal to p factorial x to the p plus n. And then the bottom is p plus n factorial. P plus n factorial. Okay. Now I'm gonna rewrite it as in terms of the gamma function. So this right here is gamma of p plus 1 divided by gamma of p plus n plus 1 times x to the p plus n. So I'm ready to box this. So this equation here is, let's call that number 16. Equation 16. All right, so what happened if you have a mixture between negative value and positive value? So let's go with the easy one first. Suppose you have d m derivative on d to the minus n, and then acting on x sub p like this. What is the answer? Okay, so we would need the result for 16 and also for 15. Okay, so to prove this, we need to use equation 15 and 16. All right, so this equation here is d minus n to this is going to be gamma of p plus 1 x to the p plus n divided by gamma of p plus n plus 1. Okay, so this part right there is from equation 16. Now dm on this whole thing here, we're going to use the other equation 15. Okay, so the equation 15 is dm p. Okay. So equation 15 is this, dmxp is equal to gamma p plus 1 divided by gamma p minus n plus 1. And the power there is x to the p minus m. Okay. So let's see how can we use equation 15 on this object. here I have a dm. This dm is similar to this dm here. All this here is just a constant factor, and in fact I'm gonna rewrite that outside. So I'm gonna write gamma p plus 1 divided by gamma p plus n plus 1, and then dm on x to the p plus n. Okay, so use equation 15 on this. Okay. So this is equal to gamma p plus 1 over gamma p plus n plus 1. dm, this is the same thing as gamma p plus n plus 1. Okay, because this p here is now p plus n. Okay, and then the bottom one is p minus m plus 1. So the p downstairs is divided by gamma p plus n minus m plus 1, and then x to the p plus n minus m. Okay. Whew. All right, so you see here, this gamma function cancels this gamma function, and so we left with x to the p plus n minus m. We left with the gamma of p plus 1 divided by gamma of p plus n minus m plus 1. Okay, now this is equal to dm d minus n f of x. Oh, x of p. So I'm gonna box this. Equation 17. Alright guys, so I think I will stop here today. The video is longer than I expected. Next time I will show you the result and compare the result from 19th century calculus versus the 21st century calculus, including more information that we can extract from the problem. Okay, have fun guys.